Shaowu will be presenting material on his completed DTC visitor program project. So just looking back at Shaowu's history, so he received his bachelor's degree in atmospheric physics from Nanjing Institute of Meteorology, followed by his master's degree in atmospheric science from the Chinese Academy of Meteorological Sciences. And then he completed his PhD and a postdoc in atmospheric science from North Carolina State University. And so Shaowu is a familiar face in the DTC as he's worked at NOAA GSL and at the University of Colorado on DTC projects under what was the hurricane task at the time, working on the HWRF model. And then in 2013, he returned to the Carolinas where he took a faculty position with Coastal Carolina University. And so today, Shaowu will be presenting his seminar on evaluating the HAFS microphysics schemes using GOES-R satellite imagery for Atlantic hurricanes or Atlantic Basin hurricanes. So with that, I will hand it over to Shaowu to get started.
Thank you, Catherine, for the introduction. Let me share my screen. So can you guys see my screen?
Yes, we can. If you can just put it in full screen, it should be good.
Hey, and put it in a slideshow mode. Okay, so thank you everyone. Good morning. Thank you for coming to this talk. Topic is evaluating the HAFS model microphysics schemes using GOES-R satellite images for Atlantic hurricanes. And this is supported by DTC visitor project. So the HAFS model is a hurricane analysis and forecast system. It's the NOAA, currently the NOAA operational hurricane forecast model. At the time of this project, there were two HAFS model configurations that were being considered for operational implementation. One is called HAFS A, and the other is called HAFS B. So the HAFS model, these two versions, they are very similar, but the main difference is the microphysics scheme. Because HAFS A uses GFDL single moment scheme, and HAFS B uses the Thomson scheme, double moment.
Shaowu, it looks like your slides aren't advancing.
Oh, maybe I'm sharing. Oh, maybe because I clicked the slideshow after I shared the screen. Let me see. Okay, I stopped the sharing, and then let me do the slideshow. Sorry for this.
No worries, there's always something.
Let me try again.
Okay.
How about now?
Yeah, I can see it. It looks quite small, but maybe
Quite
that's
small?
Yeah, no, I think you're good. We're getting a thumbs up. So go ahead. Thanks.
Okay. Yeah, I was talking about the two versions of the HAFS model. There are some other differences, but the main difference is the microphysics. And the motivation, because we know historically, the HWRF and the HAFS model, they undergo a lot of the evaluations using the track and the intensity, longitude, latitude of the storm center, and the maximum wind. However, there is another need to use the QPF, the rainfall, the precipitation forecast. And the evaluations using just the track and the intensity are not very useful for the precipitation forecast evaluation. And so the QPF performance of HAFS is still not very clear. This gap is largely due to the lack of the physics-based or process-based evaluation, which is in turn is due to the rare direct observation of the hydrometeors, like the cloud field, the rainfall ice fields. So to address this gap, we will use the satellite images, and we run the model results through the CRTM model to turn them into the synthetic satellite images. Then we will compare the synthetic images with the observed images and compare these two models. Okay, so slide. So in this study, we used the 3 hurricanes. All of them are in 2023. Hurricane Lee, Hurricane Idalia, and Hurricane Ophelia. They are all Atlantic basin hurricanes. So the goal is to assess the effect of the 2 different microphysics schemes, GFDL and Thomson. The effect of these schemes on the hydrometeor simulation or forecast the scale of the 2 HAFS model versions. And so to provide recommendations on how to further improve the models, especially the microphysics. And the key objectives, we will obtain the data, the satellite images, and the HAFS A and HAFS B simulations. And we pre-process them, basically to regrade them into the same grade. So the target grade is about 6 degrees by 6 degrees, and the resolution is 0.06. So for each storm, we will have 200 by 200 grid points. And we will feed the model result into the CRTM to create the synthetic images. And after that, we will use several verification methods to evaluate them. So the verification method includes the PDF, probability density functions, and the composite images, and the target diagram, a Taylor diagram, and fraction scale score, and the equitable threat scores, so ETS. The outcome will try to pinpoint the microplastic biases, caused biases in the forecast. So I want to give you an idea of how the data look like. So you see the 3 images. They are the HAFS A on the left, HAFS B in the middle, and the observation on the right. So these are for a time snapshot for Hurricane Lee. The observation sensors, we use the infrared at the wavelengths of 10.3 micrometers. And the coverage is a 5 minutes interval full disk. So this is the data is globally covered. So the sensors native resolution is about between 3 to 5 kilometers. But again, here we interpolated them all into the same grade with 0.06 degree resolution. Hey, CRTM. So the purpose of CRTM is turn the HAFS model result into synthetic images. So the input include the temperature profile, and water vapor profile, surface properties, land use, and most importantly, we have the cloud, ice, snow, rain, and global mixing ratios, and the corresponding optical property tables that are matched to HAFS A, GFDL, and HAFS B, the Thomson schemes. So the matched optical property tables are used in this study. And we used the CRTM Python interface in this research. Okay, so quick list of the evaluation methods. Probability density function is basically is a histogram. It's like a histogram graph. And the composite images, Taylor diagram, target diagram, FSS, ETS. So I will be showing the results from all these different verification methods. So we'll start from the PDF. So this figure you see, we used all the available model data, forecast data, and 3 storms, Ophelia, Idalia, and Lee. So the brightness temperature ranges from 180K to about 300K. From this PDF curves, you can see both models, HAFS A and HAFS B, they have a higher frequency on the cold cloud, cold temperature end. And this here, I'm not sure if you guys can see my mouse point. Okay.
Yes,
Anyway.
we can.
Yeah, okay. So you can see this is observation. Here is HAFS A, and this orange is HAFS B. From all these 3 PDFs, you can see those models tend to have a higher frequency here, higher frequency here on the cold temperature side, and underestimate the frequency on this warm temperature side here. And if you compare HAFS A and B, clearly you can see the HAFS B, which is this orange color. It has a higher bias. It has a higher frequency here, very, very big difference here. So the result shows that the HAFS A, HAFS B, they overestimate the higher and colder cloud tops than observed. And the HAFS B seems to have a more severe bias than HAFS A. Now let's move on to the composite images. What are these composite images? Basically, we overlay all the available data onto one image. So these images, these composite images, they represent the mean hurricane, the mean storm view. And the benefit is, at each time there are a lot of noise and random errors. So by adding all these different times together, hopefully the noise cancels each other. So we have a more systematic view of the brightness temperature of the hurricanes. Also, because I have been looking at all these like several thousand of images, and there's really impossible to draw systematic conclusion from these thousands of individual images. Anyway, on this image, you see this, the first row is Hurricane Idalia, and then Hurricane Ophelia in the middle, and the bottom is Hurricane Lee. And the left column is HAFS A and then HAFS B in the middle, and the observation is on the right. So a few things we can see from these images, these composite images. One is that both HAFS A and HAFS B are able to capture the mean vortex structure and the cold sector. So for example, in this Hurricane Idalia, we can see the cold areas, the cold clouds are located, on average, are located on the located in the northeastern quarter of this domain. And the same thing happened in the observation. We can see in the observation. And for the Hurricane Ophelia, the cold areas are on the north and the northwest, which is consistent with the observation. And for Hurricane Lee, it's most symmetric. The vortex structure is the most symmetric for both the models and the observation. However, we can see that from these images, we can see both models, they tend to have a darker color than the observation. Because we use the same color scale for all the images here. And for Ophelia, Idalia, and Hurricane Lee, we see the models darker in the color. And if you compare A and B, you can see the HAFS B seems to be even darker than HAFS A. So this is consistent with the PDF comparison, indicating that the HAFS B seems to have a larger cold bias than HAFS A. So this slide is also a composite image, but this is for one valid time snapshot. And this valid time is when these three storms reached their peak intensity. So for the observation, of course, there is only one image, but for the model, because we have multiple focus for the same valid time, so these model images are still composite images. And we can see the same pattern. And the model can capture the basic structure, the main structure of the hurricane vortex. But here we can see, again, it seems the model is generating more higher cold cloud areas than the observation. And clearly you can see the observation images have more warm areas indicated by the yellow warm areas than the models. So this is again consistent with the earlier conclusion about the models overestimating the cold cloud areas, and the HAFS B is more so than HAFS A. By the way, if you guys have any questions, feel free to let me know, interrupt me so we can discuss. And now we move to the so-called target diagram. So how to read the target diagram? The target diagram, it separates the errors into a bias and the unbiased root mean square deviation. So the x-axis shows the unbiased RMSD, and the y-axis shows the bias. So if you see the model is, all the models are below zero on the y-axis. So that means all the models are showing a negative bias, a cold bias in terms of the brightness temperature. And for the unbiased RMSD, they are similar. So they have similar unbiased noise. And you compare HAFS A and B, the red plus is HAFS A and the blue circle is HAFS B. So clearly you can see the HAFS B has a larger code bias. It's more negative, so it has a larger code bias than HAFS A. The same thing, but for Hurricane Idalia, we can see the same pattern. All the models are having a code bias, and the HAFS B, the blue circle, is having a larger bias, larger code bias than HAFS A. And they have similar unbiased RMSD. The same thing for Ophelia. And Ophelia is a little bit different than the other storms. So if you look at the 24-hour forecast and 48-hour forecast, you can see the results are very, very mixed, very mixed. However, we see the same bias, larger bias for HAFS B after 60-hour forecast. But we can see both models have a code bias. Anyway, they are negative on y-axis. But it's just for a range of the forecast time, HAFS A and HAFS B are quite mixed. They are almost on top of each other. Now we look at the Taylor diagram. So the Taylor diagram, we'll see from the angle, you see the correlation from 0 to 1. And the larger the better. And the black contours show the standard deviation, sigma standard deviation. And you see this blue curves. The center of the blue curve is observation. So observation has a correlation of 1 because it's itself. And has a standard deviation, particular standard deviation of the observation. For the models, the closer the models to the green center, the closer the model is to the observation. So now let's look at by the way, one thing we should notice, the Taylor diagram is after the bias is removed. So all the things you see from the Taylor diagram is for the unbiased RMSD. So this is the Hurricane Lee. So we can see the red one is HAFS A and the blue triangle is HAFS B. And we can see for all the forecast lengths, HAFS A is closer to the observation, the green center. And largely because HAFS A is having a higher correlation than HAFS B. HAFS B is less than 0.7 and HAFS A is greater than 0.7 in terms of the correlation. And the sigma are similar between HAFS A and HAFS B. They are both around 30K, except for the 72 focus hours. 30K, 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 but at 42 focus hour, it jumped to, oh, it's still 30. Yeah, that's still 30. Anyway, sorry. It is still the standard deviation is still 30. So that's similar. The Taylor diagram for Idalia, this is a little bit different because now the HAFS A and B, they seems to have very similar correlations at all focus times. Although the HAFS A is slightly better than HAFS B in terms of the correlation. But it seems the HAFS A is having a smaller standard deviation than HAFS B, and the smaller standard deviation is closer to the observation. So that explains why HAFS A is having a smaller unbiased RMSD than HAFS B. Taylor diagram for Ophelia. And we can see for 24-hour focus and 48-hour focus, the distance of HAFS A and B to the green centers observation, they're almost same. They're almost same here. And for 48 hours, actually the HAFS B seems to be very slightly closer than HAFS A to the green centers observation. But for 60 hours and 72 hours, again, the HAFS A shows a much better, closer to the observation than HAFS B. There is a range of the time, focus time, when the HAFS A and HAFS B, they are very, very similar, mixed. Now we look at the FSS, the fraction skew score. In case you are not familiar with FSS, it's a neighborhood verification method. So you divide your domain into some larger neighborhood sections and compare some variables, some conditions. For example, in this analysis, we look at the brightness temperature greater than a threshold. So we look at in this neighborhood, we look at the brightness temperatures that exceeds a certain threshold. And the benefit of this neighborhood method is it rewards correct spatial structure rather than a point-to-point match. So it can tolerate some point-to-point mismatch, but have the similar structures. Anyway, in this verification, we use the 5 grid by 5 grid neighborhood. So for each grid point, for each model, we count the heat and the means in the 5 by 5 grid neighborhood. So, and we use the threshold from 270 for the warm cloud all the way to 260, 250, 240, and 230. And we plotted HAFS A using solid lines and HAFS B using dashed lines using the same color. So from this figure, you can see for all this threshold, the solid lines have a higher score than the dashed lines, the yellow, the green, blue. So that indicates that the HAFS A is having a better neighborhood matched structure than HAFS B. for all the threshold. And we can also see that for the 230K threshold for a very cold cloud, and the skew score quickly decreased to nearly zero for 120-hour forecast. And for the different threshold, we can see that the colder the threshold, the worse the skew score. So that's understandable because it's challenging to predict where the cold clouds are located. But again, the conclusion is consistent with earlier analysis that it seems the HAFS A is better than HAFS B in terms of the fraction skew scores. The same thing for Hurricane Ophelia. But the Ophelia, you can see that in the middle of the forecast length, from 24 to all the way back to 60, you can see the results are really mixed. The HAFS A and HAFS B, there's no clear signal of which is better. But this is consistent with the earlier evaluations. If we look at the earlier Taylor diagram, you can see the Ophelia during this forecast, the lengths of 24 and 48, the results are very, very close. And if we look at the target diagram, Ophelia, so these results are really close. The same thing we can see from the fraction skew score too, that the results are very mixed. So this is the fraction skew score for Hurricane Idalia. So the results are basically similar to the result for Hurricane Lee, which shows that the HAFS A is again consistently shows higher score than HAFS B for all the skews, for all the threshold. And also similar to the Hurricane Lee's result, colder threshold show worse FS score. And for Hurricane Idalia, basically there's no focused skew for the cloud locations structure for cloud colder than 230K, basically. All the scores are zero here. Let's see. Another thing we looked at is called the equitable threat score, ETS. The ETS is for different thresholds. We use the heat minus the expected heat, the random heat, divided by the heat plus the miss plus false alarm minus the random heat. This is for Hurricane Idalia. We can see the conclusion are similar to the result by the FSS. We can see for all the threshold, HAFS A, the solid lines, show a better score than HAFS B, significantly, especially in the earlier forecast lengths, so shorter forecast lengths. And again, the skew score, the skew for 230K cold areas, basically is 0. And for the other threshold, 240 and 250, they quickly decline to 0 skew score or longer focus lengths. But in terms of the comparison between A and B, Obviously, again, it's HAFS A consistently having a higher score than HAFS B. This is the same thing for Hurricane Lee. Again, we can see the solid lines are all having a higher score than the dashed lines. HAFS A better than HAFS B. And for Ophelia. And for Ophelia, you can see after 20 hours, we can see this very mixed skill scores between A and B. They are almost on top of each other, a lot of noise. And the 230K score is basically 0. And we can also see the quick decline of the skill with the forecast length. So from all these verification methods, we can see the main conclusion is it seems HAFS A, which use the DFDL microphysics, consistently outperforms HAFS B with the Thompson skill. And this is consistent from all these verification methods. Another thing we can see is it seems both models overestimate cold cloud coverage and height. We can see the cold bias in this brightness temperature. But the good thing is both models can effectively capture the general structure of the vortex. So the asymmetric structure are shown in the model simulations. And despite the HAFS A's better skill, both models show skill degradation at longer focus lengths and a lower threshold. So that indicates a lot of room for improvement. And I want to mention some uncertainties in this study. First is the configuration difference. Between HAFS A and B, the major difference is the microphysics, but there are some other differences. For example, the boundary layer scheme and the data assimilation and the entrainment tuning between these HAFS A and HAFS B. So they are not entirely same besides the two microphysics schemes. Another uncertainty comes from the CRTM because potentially there are some mismatches between the model microphysics and the CRTMs. We use optical property assumption. These matches, these optical property tables we use. We use the DFDL and the Thompson scheme, but the tables for DFDL and the Thompson schemes. But because the Thompson scheme, the model results, the model output don't include the concentrations of the ice, the numbers focused. So we had to use the table. So that may introduce some uncertainties. Another thing is because the model runs are all cycled runs, so they are not cold start runs. So in some cycles, the initial conditions, the errors introduced from some cycles may propagate and influence the focus in the following cycles. So that's another source for potential uncertainties. I want to thank for DTC's visitors program and all the received a lot of help from the DTC team and colleagues. So thank you very much. So that's all I have. I will welcome any questions.
Thank you, Shaowu. All right, I see Jimmy has your hand up. Go ahead, Jimmy.
Yeah, that's very interesting talk. One thing I was wondering there was if there's a time, a forecast length dependence on the bias. You see this cloud bias, because that would tell us whether the clouds are too long-lived or something like this. So it'd be interesting to know if the bias of the cold bias was changing with time. Okay.
The target diagram shows the bias and the change with time.
So it isn't really changing much with time.
Yeah, there's no clear pattern.
Right.
It's the bias and the time. And this is for Lee, and let's see it for Italia. It seems the bias is actually smaller for longer forecasts.
Okay.
Yeah.
Do you have any hypothesis for? Well, I guess the other uncertainty is the CRTM itself, whether this is a true bias or or not. I guess. Do you have any hypothesis for why the? I guess these microphysics schemes are very simple, the way they treat ice.
Yeah. I don't have a hypothesis at this time.
Right.
For this project, we actually hope to do some diagnostics, but we haven't got there yet.
Okay, thanks.
Thank you.
Any other questions for Shaowu? Or maybe I'll ask one while others are thinking. So generally, it seemed like the HAFS A performance was generally better relative to HAFS B, where you were seeing more of a cold bias in the HAFS B relative to HAFS A. This is interesting because you were looking at the version 1, right, that has the HAFS A with the GFDL and the HAFS B with the Thomson Microphysics. But going forward with HAFS V2, the Thomson Microphysics was used in both configurations. So I'm curious if you have any thoughts or speculation as to why the GFDL microphysics tended to perform better, or if you have thoughts on perhaps where you may have next steps for isolating and diagnosing, where there could be some improvements to the Thomson microphysics.
I don't have I don't have a hypothesis at this time, but I want to say that for choosing the schemes, I think a lot of decision is made according to the track and intensity errors, right? And sometimes, if we want to forecast, for example, the precipitation more accurately, we may need to go beyond the track and intensity error only and look at the other more physics-based verifications. But hopefully we can, in the future, we can do some diagnostics to give us some insights about why GFDL is showing a smaller bias, but it may have a larger track and intensity errors, if I assume. Yeah, so these two kind of verifications, they don't always match. Meaning a less track and intensity error doesn't always mean more realistic physics simulations, I guess. Did that answer your question, Catherine?
Yeah, it did. Thank you. Biswas.
Hi, Shaowu. Great
Hi,
talk.
Biswas.
Hey, I was wondering, you have done similar, evaluation with the HR model, right? I remember you had the fractional skill score you did with HWARP. Did you see any changes, like improvements with the HAFS A or B compared to HWARP?
Okay. I have to be honest. I don't remember the details about the specific verification results with HWARF. We can compare. We can go back to compare the HWARF verification result and compare with HAFS. But I don't remember very evident significant difference between these
Okay.
two.
Yeah, because I remember, when you showed Hurricane Lee,
Mhm.
for the cold temperatures, and my memory is also bad. I think for cold temperatures, I think I've seen similar trends, but I don't remember exactly whether it was with the observed or with the model, the higher bias. Okay, but great talk. Nice seeing you.
Okay, thank you.
Any other questions for Shaowu? All right. Well, if not, let's thank Shaowu. Maybe virtually some applause here. Thank you very much, Shaowu. It's been great working with you, and we appreciate you taking the time to give this seminar.
Thank you. Thank you for all the support and help.
All right. Take care, everyone.
Take care. Thank you again. Bye-bye.